In this section of electrical measurement, we will talk about Wheatstone Bridge. The discussion will include Wheatstone Bridge, what is it, working principle of a Wheatstone Bridge, derivation of balanced equation of a Wheatstone Bridge, modification of the fundamental bridges, strain measurement using Wheatstone Bridge as a light detector, and applications of Wheatstone Bridge, limitations of Wheatstone Bridge, error sources in a Wheatstone Bridge. The Wheatstone bridge works on the principle of null deflection, that is, the ratio of their resistances are equal and no current flows through the galvanometer. Wheatstone bridge or the resistance bridge finds application to calculate the unknown resistance by balancing the two arms of the bridge circuit, in which one consists of a standard resistor and the other the unknown resistor under measurement. The bridge was invented by Samuel Hunter Christie in the year 1833, which was later popularized by Sir Charles Wheatstone in 1843. The bridge has four arms comprising two known resistors, one variable resistor, and one unknown resistor. The four arms are connected through a galvanometer which is to be balanced by null deflection. The bridge is very reliable and useful when it comes to low resistance measurement. The known resistors are generally in the ratio of 1:1 or 10:1 or 100:1. The variable resistor is a potentiometer or a rheostat with a range of 1 to 10,000 ohm. As already told, the Wheatstone bridge works on the principle of null deflection. That is, the ratio of their resistances are equal and no current flows through the circuit. Under normal conditions, the bridge is in unbalanced condition where current flows through the galvanometer. The bridge is said to be in a balanced condition when no current flows through the galvanometer. The condition can be achieved by adjusting the known resistance and the variable resistance. The current enters the galvanometer and divides into two equal magnitude currents of I1 and I3. The bridge is balanced by adjusting the variable resistor to balance for the unknown resistance Rx that is under measurement. The equation to determine the unknown resistance while the other resistance values are known is given as Rx equal to R2 by R1 whole into R3. Given alongside is the circuit diagram of a Wheatstone bridge, where we see that there is one DC voltage source and there are four terminals marked as A, B, C and D. The resistance in the four arms are R1, R2, Rx and R3 respectively. The currents are I1, I2, Ix and I3. At balanced condition, the values of both voltage and the current between the midpoints B and D are 0. Therefore, I1 is equal to I2, I3 is equal to Ix and Vd is equal to Vb. Thus we get Vdc by Vad equal to Vbc by Vab, which translates to I2 R2 by I1 R1 equal to Ix Rx by I3 R3. Solving we get Rx equal to R2 by R1 whole into R3. Applying Kirchhoff's current law at points B and D, we get I3 minus Ix plus Ig equal to 0 and I1 minus I2 minus Ig equal to 0. The entire expression is marked as equation 1. Applying Kirchhoff's voltage law at ABDA and BCDB loops, we get I3 R3 minus Ig Rg minus I1 R1 equal to 0 as equation 2 and Ix Rx minus I2 R2 plus Ig Rg equal to 0 as equation 3. At bridge balance condition, Ig is equal to 0. Therefore, equations 2 and 3 become I3 R3 equal to I1 R1 and Ix Rx equal to I2 R2. Dividing the modified equation 2 by equation 3 modified, we get Rx equal to R2 I2 I3 R3 whole by R1 I1 Ix. As I3 equal to Ix and I1 equal to I2, we get Rx equal to R2 by R1 whole into R3. Few modifications of the Wheatstone Bridge are as follows: Caddy-Foster Bridge for measuring small resistances, Kelvin Double Bridge for measuring small 4-terminal resistances, Maxwell Bridge and Wine Bridge for measuring reactive components. These variations of the Wheatstone Bridge enables it to measure impedances, capacitances and inductances. A Wheatstone bridge can be arranged to measure strain. Stress is the force applied to a material divided by the material's cross-sectional area. Strain is the deformation or displacement of material that results from an applied stress. The resistance of strain gauge varies with strain applied on them. This property is applied in measuring the strain and hence stress on any surface. The range of strain gauge resistance is from 30 ohm to 3000 ohms. The galvanometer is balanced to get a zero reading by adjusting the rheostat, and the variable resistor measures the applied tension or compression on the strain gauge. With no force applied to the strain gauge, rheostat is varied and finally positioned in such a way that the voltmeter will indicate zero deflection. This is called a bridge balancing condition. The resistance value of the strain gauge increases or decreases with it being tensed or compressed, causing an imbalance in the bridge circuit. This provides a voltage indication on voltmeter corresponding to the strain change. Below figure shows that the strain gauge is fixed at the unknown resistor arm of the Wheatstone bridge circuit. A Wheatstone bridge can be arranged to measure the light intensity. An LDR or light dependent resistor is a passive sensor converting incident visible light into corresponding resistance value. The LDR is generally made up of cadmium sulfide CDS photocell. The LDR has negative resistance coefficient, that is, the resistance decreases with increase of light intensity. LDRs are put in Wheatstone bridge circuits to measure incident light intensity. CDS cells have resistance in megaohms range in absence of light, and the resistance decreases with the increase of light intensity expressed in lux. Given here is the arrangement of measuring light intensity using a Wheatstone bridge. We see that the LDR is placed on the unknown resistance arm of the Wheatstone bridge, and in place of the galvanometer we have applied an op-amp 741. The LDR photocell is connected into the Wheatstone bridge circuit. The op-amp is connected as a voltage comparator with the reference voltage Vd applied to the non-inverting pin. The potentiometer Vri sets the trip point voltage Vc applied to the inverting input and is set to the required nominal light level. The LDR photocell is connected into the Wheatstone bridge circuit. This arrangement can be used as a light sensitive switch as well. The applications of the Wheatstone bridge are as follows: for precision measurement of low well resistance, measurement of physical parameters like light, strain and temperature when coupled with operational amplifiers, measurement of impedance, capacitance and inductance using variations of the Wheatstone bridge. Wheatstone bridge has few limitations as cited below. Lead and contact resistance values become source of measurement error. The galvanometer becomes insensitive to imbalance when very high resistance value is measured. The heating effect due to the constant current flow changes the resist value, giving rise to faulty results. The following are the error sources in a Wheatstone bridge. The difference between the true and the marked value of the three resistance can cause the errors in measurement. The galvanometer is less sensitive, thus inaccuracy occurs in the balance point. The resistance of the bridge changes because of the self-heating, which generates an error. The thermal EMF causes serious trouble in the measurement of low value resistance. The personal error occurs in the galvanometer by taking the reading or by finding the null point. For more detailed reading, the viewers can refer to the following links. Thank you.